Hi everyone. In this screencast, I'm going to be talking about dipole-dipole forces. And we learned last unit that some molecules are polar because of their shape. And polar molecules have a dipole. And our definition of a dipole is an unequal distribution of electrons. What we're going to learn today is that polar molecules that have a dipole can attract neighboring molecules through dipole-dipole forces. So these are the attractive forces between polar molecules. So let's think about this. If we have two molecules of hydrogen chloride and we want to show the dipole-dipole force between them, how would we draw that? Last unit, we learned how to draw hydrogen chloride. We learned that hydrogen chloride looks like this. And we learned that there's a partial positive on the hydrogen and a partial negative on the chlorine. Same thing here. If I were to draw a neighboring hydrogen chloride, I'd have a partial positive on the hydrogen and a partial negative on the chlorine. Well, because of oppositely charged things attracting each other, this slightly negative chlorine will attract the nucleus of this hydrogen. And this dashed line here represents a dipole-dipole force. That's shown here as well. We have a dipole-dipole force between a chlorine and a hydrogen in neighboring molecules. Right? We don't want to confuse our dipole-dipole force, which is an intermolecular force, with our polar covalent bonds. Okay, so we've already learned about dispersion forces. How do dipole-dipole forces compare to dispersion forces? Well, dipole-dipole forces are found in polar molecules, whereas nonpolar molecules only have dispersion forces. And dipole-dipole forces are stronger than dispersion forces. So what does this mean? Well, it means that polar molecules are going to have stronger forces of attraction between them than nonpolar molecules in general. Let's look at how polar molecules might be aligned in a substance. If we have a solid that consists of polar molecules, then our molecules are going to be locked in place, but the positively charged part of the molecule is going to be adjacent to the negatively charged part of the molecule. And this happens when water freezes. Our positively charged hydrogens end up next to our negatively charged oxygens. When water is a liquid, however, the particles are now moving, but they will still attract each other just like they did when they were in the solid. So we'd have positively charged hydrogens attracting negatively charged oxygens. The difference here, again, is that the particles are moving around. Let's take a look at a question. Predict which one of the following would have a higher boiling point, fluorine, F2, or HCl. Take a second to think about that. So we want to think about which of these substances has stronger intermolecular forces, because when we boil a substance, we are breaking the intermolecular forces between molecules. We are freeing molecules from the liquid. And what we should recognize is that fluorine is a nonpolar molecule. If we were to draw fluorine, we would see that it's symmetrical. Whereas HCl is a polar molecule, hydrogen chloride. And this means that fluorine only has dispersion forces, but hydrogen chloride has dipole-dipole forces, which are stronger. And if they're stronger, they're going to be harder to break, giving HCl a higher boiling point. Okay? And if we actually look at the numbers, we can see that HCl's boiling point is 183 Kelvin, whereas fluorine has a boiling point of 85 Kelvin, a much colder temperature. Sometimes you'll see the word van der Waals forces used. Van der Waals forces just refer to both dipole-dipole and dispersion forces. It's sort of an umbrella term, meaning that it can refer to both dipole-dipole and dispersion forces.